All right. In the allylic bromination that we did in chapter 15, we would treat an allyl species with NBS and some radical initiator, light or heat, and it would brominate in the allylic position. So what made that position special? And what we said back then was that the intermediate structure was an allylic radical, and that was stabilized through resonance. So we said, oh, this carbon has radical character, so does this carbon over here. And we've been able to kind of talk about this concept just by drawing resonance structures throughout everything up until now. And now we're really getting at the heart of things, where it's not that it's this resonance structure and then it turns into this resonance structure. Resonance structures aren't real, right? They are the hybrid of the whole. What it really is it's 3 carbon atoms with 3 p orbitals, and they are overlapping, and they all have that radical character. So what we're showing here is that this radical was actually conjugated throughout that p orbital, and that's what made it extra stable. That being said, the next question is which would be more stable of the next things? Which would be more stable? So on one hand we have that, on the other hand in your packet we have that carbocation. So we have 2 different carbocations. Pause it, decide which one would be more stable. All right, you unpaused. I hope that almost all of you said that this one would be the more stable carbocation species. They both look primary, right? But this one is delocalized. It has this pi bond here that is going to share electron density with the empty orbital there, and we can draw that with resonance structures to show that not only that carbon has the carbocation character, but also that carbon. And just like we did it with the radical above, we can show this through either the resonance structures or by drawing all 3 of the carbons out and showing that they're overlapping with that carbocation character. Again, what would the resonance hybrid look like with these? We've drawn resonance hybrids in the past. It would be a partial double bond on all of those positions with partial positives showing on both of those carbons. So it shows kind of the true nature of the molecule. This is the allyl cation. So this is an allyl cation. So it's an allylic cation, has a positive charge. And that's what's really going on when we draw these resonance structures. That helps us understand it. That really does tell us like the essence of what's going on, but conjugation is telling us the actual physical nature of that carbocation, how it is split out, and how it has to do with the conjugation between the empty p orbital and the pi bond adjacent to that. Great. So that is conjugation, and we are going to learn more about that.